Welcome back to G Fun Facts Online, where we dive deep into the tech that's shaping our future. Today, we're talking about something that's going to make your current 5G connection feel like dial-up. I'm talking about 6G, the sixth generation of wireless technology. Imagine holographic presence, truly autonomous systems, an Internet of Everything connecting literally everything. Sounds like science fiction, right? But it's on the horizon, promising to operate at unprecedented terahertz frequencies. But there's a catch, a big one. The very heart of our current electronics, good old silicon, just can't keep up. It's hitting a wall. For decades, silicon has been the undisputed champion of the semiconductor world. But when we start talking about the super high radio frequencies needed for 6G, we're talking above 100 gigahertz, pushing into the sub-terahertz range. Silicon starts to sweat. Its inherent material properties, like lower electron mobility and breakdown voltage, mean it struggles with performance and efficiency at these extreme speeds. As 6G aims for terabits per second data rates and microsecond latencies, silicon's limitations in gain, output power, and efficiency become glaringly obvious. So if silicon is out, what's in? Researchers are on a quest, exploring a whole new suite of semiconductor materials. First up, gallium nitride, or GaN. This is a strong contender, especially for the power amplifiers in 6G systems. Why? It offers higher efficiency, power density, and it can handle heat much better than silicon. There's even GaN on silicon technology, trying to get the best of both worlds. GaN's performance with silicon's manufacturing scale. Recent breakthroughs show GaN can operate across wide frequency bands, meaning a single amplifier could potentially handle 4G, 5G, and future 6G systems. Think about how much more power efficient our base stations could become. Then there's indium phosphide, or INP. This material is critical when we're aiming for frequencies approaching or even exceeding 1 terahertz. Devices made with INP, like heterojunction bipolar transistors, show amazing speed, output power, and energy efficiency in this sub-THz zone. The challenge? Making INP technology mature and cost-effective for mass production, perhaps by growing it on silicon substrates. European groups like Move 2 terahertz are pushing hard to build a solid INP semiconductor ecosystem. What about gallium arsenide, or GIAs? It's another 3V compound semiconductor, known for its high-frequency performance thanks to high electron mobility. While it's facing tough competition from GaN and INP at the very top end of 6G frequencies, Gallium arsenide has a strong history in RF applications and might still find its niche in certain 6G components. Now, let's not completely count silicon out just yet, or at least its close relative. For frequencies up to around 150 gigahertz, especially for shorter range communication, current CMOS and silicon germanium, or SiG, technologies are considered pretty good. SiG essentially gives silicon a boost, extending its capabilities to higher frequencies than CMOS alone can manage. However, for those longer range applications and the really high power amplification, the 3V materials like GaN and INP still hold the edge. But the innovation doesn't stop there. We're entering the realm of truly exotic materials. Think two-dimensional or 2D materials, like graphene and other monolayers. These are materials just one atom thick. Their unique electronic and optical properties, arising from quantum confinement effects like tunable band gaps and super high carrier mobility, are incredibly promising for 6G. Graphene photonics, for example, is being explored for up and down converting high-speed data streams in the sub-terahertz range. Scientists are even stacking different 2D materials like Lego bricks to create heterostructures with enhanced performance. And if that's not futuristic enough, researchers are also looking into metamaterials, these errant materials found in nature. They are engineered structures with wild properties. They could be used in reconfigurable intelligent surfaces, or RIS, to actively steer and amplify 6G signals, boosting coverage and efficiency. We're also seeing research into low-loss dielectrics, advanced ceramics, and even less conventional options like silica foams or wood-based composites for specific 6G jobs. It sounds amazing, but let's be realistic. There are significant hurdles. Cost-effective manufacturing and scaling up production for many of these compound semiconductors are major challenges compared to the decades-old, highly optimized silicon processes. Integrating these new materials with existing silicon-based platforms, what we call heterogeneous integration, is a massive area of research. We need to make them play nice together. And, of course, ensuring these novel materials are reliable and have minimal defects is crucial before they can go mainstream. Plus, the exact performance targets for 6G are still being defined, so it's like aiming at a moving target for materials scientists. So the journey beyond silicon for 6G isn't just about a simple swap. It's a complete paradigm shift in how we design, fabricate, and integrate semiconductor devices. It requires massive collaboration between industry and academia to speed up development and get these advanced materials into the market. With 6G networks expected to start rolling out around 2030, the innovations in semiconductor materials happening right now are laying the foundation for this next wireless revolution. It's a thrilling time for materials science, and it's going to unlock a future we can only begin to imagine. That's all for this episode of G Fun Facts Online. Join us next time as we explore another fascinating piece of the future. Stay curious.